So today we finish up our last chance to do string theory. I'm writing up there a little bit of the summary of what we got to last time. So let me backtrack and review a second. We have a Neves-Schwarz sector for an open string in which you build things acting on a vacuum that is declared to have a Fermi number -1. It's conventional. And then you build states acting with alpha minus n's, the X oscillators, and the Neves-Schwarz oscillators, the fractional B's. All of these are anti-commuting, so they contribute 1 unit fermion number. Then the mass squared, by the time we reordered things, remember we have a few formulas for a normal Neumann-Neumann or bosonic coordinate. The ordering constant is -124. For Neves-Schwarz fermion is -148. And for a Ramond direction was +124. And those are things, when you will be doing this problem on the heterotic string, you can use those things. You don't have to compute things again. So these ordering constants made the Neves-Schwarz mass shift to be -1/2, and the Ramond mass shift, each bosonic coordinate was matched by a fermionic coordinate, so it was 0. Now the Neves-Schwarz sector is built by acting with these oscillators. The first state with n perp is equal to 0 is a tachyon, and you see it here. With n perp, you can have a -1/2. So the massless states are B -1/2 I on the Neves-Schwarz vacuum that also has P plus and P transfers. So these were our states, and then we wrote this generating function. And that generating function, I want to just for you to go back and focus here. The products over n1 to infinity is because you have infinitely many oscillators. These are the bosonic ones because they give a lot of things when you expand them up in the numerator. These are the fermionic ones because they start with 1/2. There are 8 of them for each case, and this is the mass shift of -1/2. In the Ramond sector, you had oscillators alpha minus n, d minus n, this mass squared, and Ramond vacua, degenerate Ramond vacua. The NS vacuum is not degenerate. This degeneracy appeared because the d zeros were 8 d zeros, 0 modes that don't contribute energy. So you can pile d zeros on the unique vacuum and get lots of states. In fact, you get 16 states because there are 8 d zeros. 8 is 4 by +4. 4 creation, 4 annihilation, 4 creations, and therefore you have 2 to the 4 possibilities for states. Each creation operator may not appear or may appear once, may not appear twice. So you get 2 possibilities for each creation operator, so 2 to the 4 states. That's 16 states. Declaring the fermion number to be something on the vacuum, then all these d zeros that you're acting have fermion numbers, so you get 8 vacua that have negative fermion number and 8 vacua that have positive fermion number. All of 0 mass. Because n, there's no oscillators on this, and perp equals 0. And then we wrote the partition function for the Ramond thing. And here you see this thing. This is the effect of the alpha n of the dn oscillators. This is the effect of the alpha n oscillators. There are 8 species and 16 vacua. So every state appears 16 times because it can appear on 16 vacua. So this is as far as we got last time. And you started practicing on this for the heterotic problem. I'll say a little bit about it still. Now, here comes a piece of numerology. So, if you have something like that, any curious physicist would just see a few numbers and see how they look. 8, 36 square root of x, plus 128x, plus 402 x square root of x, plus 1152 x squared, plus, and you do then the Ramond one, and you get 16 plus 256x plus 2304x squared. Okay, this series compares things at mass. The power of x is the mass squared, the alpha prime m squared. So this is alpha prime m squared minus 1/2. This is massless. This is alpha prime m squared 1/2, alpha prime m squared 1. So the masses are comparable. So let's compare. Well, here there's a tachyon, here there's no tachyon. 8 massless state, 16 massless state. Another fractional states that are not here. Here, 128 to 56. Fractional that are not here. 1, 152, 2, 3, 0, 4. And then you see certainly that 8 is the double of that. 256 is the double of that. And then you see, oh, this one is the double of that. So there's a matching. And then physicists said, oh, maybe we can construct a theory that can have supersymmetry, space-time supersymmetry, because all the states that we build in the Ramond sector transform as spinors. These objects are spinors of the Lorentz group. So anything that comes from the Ramond sector will transform as a spinor of space-time, as a real fermion, anything. You see, the Ramond sector has even and odd states with respect to worldsheet fermion number. But they all transform as space-time spinners. So you can get fermions in space-time from the Ramond sector. All the Neves-Schwarz things have this vector indices, so they all transform as bosons, boson representations in space-time. So we can get bosons from NS, fermions from Ramond. But we have to do one thing. We should be able to get rid of these guys, and we should be able to cut this in half. If we can do those things, it looks like it's a promising thing. So we are going to do that because this -1 to the fermion number commutes with a Hamiltonian. The Hamiltonian is basically L0, or I'll write H. And you can see that it commutes because the Hamiltonian is bosonic and always has, L0 has alpha n, or it will have B minus R, B R's, two B's that don't change fermion number, or two D's if you're looking at the Ramond sector. So it always commutes with H, so it's consistent to throw away states of definite fermion number. So what do we have here with fermion number? Well, these things, the ground state has -1 to the F equals -1. We said so. This one has one fermion in addition, so this is a +1. This has one fermion more than any state here because it's a 1/2 more unit of M perp. Therefore, this has fermion -1, this has fermion +1, this has fermion -1, this has fermion +1, which is good. We can get rid of this. So we define the NS plus sector as the NS states with -1 to the F equal +1, and we will keep those. NS plus, truncation. This is the Gliozzi-Shirk-Olive GSO projection, it's called. GSO for Gliozzi, Shirk, and Olive. And in the Ramond sector, well, we may remember from last time that you had the Ramon states, and there were things that were fermionic, things that were bosonic, but they were matching exactly in numbers. There was some sort of supersymmetry in 2 dimensions. So what we can do is say, again, in the Ramon sector, we're going to keep some states, and conventionally people say R minus, which is the Ramon states, with -1 to the f equals -1. So that you could keep, for example, RA, these states, those 8 states, and then at the first excited level, you could keep alpha -1 I on RA. You could keep D -1/2 I, D -1/2 J on RA. Oh, I'm sorry, what am I talking about? D -1 I on RA bar. These are integers. So this is negative. This is because alpha commutes with -1 to the f. This is still -1. This doesn't commute. That's why I switched to the other vacuum. And we keep those. And the effect of this is truncate things by half. So now I'm going to try to consider the partition, we call it something partition function or generating function of this Ramon and Neves-Schwarz sector. So let's do this here. Okay. So what do we want to do for the NS sector? We are keeping the states with -1 to the f equals +1. So we keep states with an odd number of b's. The 8 states up there have 1 B. The 128 states in there have either 3 B's or 1 B. And you know, the odd numbers of B's, because the mass is shifted by 1/2, represents integer values of alpha prime m squared. So we want to keep things with odd number of B's. So I want to generate this function. So look what I'm going to do. I'm going to take this same function, 1 over square root of x, pi n equals 1 to infinity. Let me write it here. Don't copy it yet. I want to make something so that whenever I have an odd number of b's, I could subtract those states. I want to take away these terms from the generating function that have those square roots there. So what I'm going to do is the following. I'm going to put here a minus. Each of these terms, this x comes from a fermion. So I'm going to have here that all these terms that I got here, they're going to count exactly the same, but the signs are going to change. Because this factor appears just like that. So signs are going to change in the terms. And the signs are going to change whenever you have 2 of these. Whenever you have an odd number of these x's that you're multiplying, and you have a minus sign here, the sign of that term is going to change. If you have an even number of these x's contributing, which corresponds to an even number of b's, the signs don't change. So since I want to keep only the states with an odd one, the odd ones change sign, so I put a minus here. And therefore now in this thing, the odd ones don't change sign, and the ones with even numbers of b change sign. So I'll take the original one, subtract this. So I have the pi n equals 1 to 8, to infinity, I'm sorry. 1 plus x to the n minus 1/2 over 1 minus x to the n to the 8. And I have the 1 over square root of x, so I'll put that in front. This 1 over square root of x. I'll put this here, take that out. And now the ones with odd number of x's that get a minus sign from here, extra minus sign, will add to the ones in here, so I get twice as many. So I must put a 2 here. And the ones with an even number of b's will cancel out. So this is the new generating function for ns plus. And now you go to the other one, Ramond. So in the Ramond, the truncation is very simple because we just take half the states. On each side, there are equal number of states. So we can put here an 8 pi n equals 1 to infinity of 1 plus x to the n over 1 minus x to the n to the 8. And that's the Ramond minus for generating function. And we've sort of seen that the first 3 numbers work out okay. And there's a matching of these two things. These two series are the same, so we can wonder if these two things are the same. And you can try it. Junji told me that he tried how many terms?
100 orders.
How many?
Up to 100 orders.
100. And they work. So without computers, a great mathematician of the last century, Carl Gustav Jacob Jacobi, proved this identity. And it apparently came out of thin air because he wrote in this book, "This is a very strange identity." It's a famous quote nowadays. It's in Latin. And basically, he just didn't know what it was good for. And well, how many years later? This was 1829. Jacob Jacobi, German mathematician, wrote his treatise on elliptic functions. Was published in 29. Maybe the research was earlier. But nevertheless, this formula nowadays is considered the keystone formula that shows there is supersymmetry. Because if you wanted to prove there is supersymmetry, you need to prove that these coincidences keep happening, and proving this formula is not that simple. But it's true. June?
Yeah, what is the motivation for choosing R minus and not R plus?
It's convention. No, absolutely no motivation. Yes?
One of the motivations is to kill tachyons.
I can't hear you.
One of the motivations is to kill the tachyon.
Well, killing the tachyon, there's good motivations. Tachyons mean that you construct theories with instabilities. So if you can get rid of the instability, it's very good. So killing the tachyon is a very good thing. Now, it's not like it's inconsistent if you keep the tachyon. There are superstring theories that don't have supersymmetry that are built with tachyons. So this is your choice. You want supersymmetry. The Ramond sector has no particle at negative mass squared. So if you want supersymmetry, the Ramond sector says no, nothing there at negative -1. So you cannot have supersymmetry and the tachyon. So that's this thing. I want to now move on to a bit of closed superstrings. So what is closed superstrings? How do they go? Oh, well, I should say, the massless sector of this theory has those, that's probably important. The massless sector of this theory that we've constructed has, in the Ramon sector, in the Neves-Schwarz sector, has B minus I, 1/2 NS, P plus P transverse. And this is a Maxwell field. In the bosonic string, it appeared as alpha minus 1I of P plus P transverse, but it's the same thing. The states have this momenta transform under Lorentz group as that. So these states generate Maxwell fields. And the RA states is a fermion, Weil-Majorana fermion. So the massless sector, massless m squared equals 0, m equals 0 for all of this. That theory has a spinor and it has a Maxwell field. Okay, let's go to superstrings, closed superstrings. So, in principle, closed superstrings is very easy once you have the picture of the open superstrings clear in your mind. But now we're going to start mixing things. So it gets to be more fun, as you will appreciate as well when you do the heterotic problem. So basically, what is it about closed strings? Well, you had in bosonic things, you had the alpha minus n, and then you had the alpha bar minus n. And the states of the closed string are like a tensor product of these states. You have any state of the open string here, any state of the another open string that you call bars, and you put them together so you have things with alpha and alpha bars acting on a new vacuum. So you're tensoring these states. For any state of the open on the left and an open on the right can be put together only if L0 is equal to L0 bar. Remember, there's a level matching condition. So when we make closed superstrings, now you say, okay, what can I put on the left? Well, I can put an NS sector, because it's super. Everything is super. On the right, I'll put an NS. That's one sector of closed superstrings. We call the NS-NS sector. People call it like that. Then you can put on the left side, we call the first one the left, which are the bar oscillators, and this is the right. That's, of course, convention again. You could put NS and you can put a Ramond here. You can put Ramond and you can put NS. Or you can put Ramond and you can put Ramond. So closed superstrings have 4 sectors. Two open superstrings have 2 sectors, but closed superstrings have 4. Now, the Ramond sector of the open superstring gives you fermions. The NS sector of the open superstring gives you bosons. Here, this is a sort of boson from the left and boson from the right. These are going to be bosons. Here is boson on the left, but fermion index on the right. Well, that's it. Once you have a spinor index, you're a spinor. This must give you fermions. This also must give you fermions. And this has 2 spinor indices. It's like 2 fermions together. Group theoretically speaking, or in terms of a bound state of 2 fermions, that's a boson. So you're going to get bosons from Ramon. These are the most complicated bosons in the world. They make us scared when we look at Ramon fields, and people recoil with panic. They're complicated. You know, we have a Nambu-Goto action, a nice action for the X fields. There's nothing that simple for the Ramon-Ramon fields. They are the key thing to many things, that they're extremely subtle. And they make superstring theory interesting. This is the basis of the ADS-CFT correspondence hinges on these Ramon-Ramon fields. They have to do their job in type 2 strings. This type 2 strings that is dual to Yang-Mills, it's full of Ramon-Ramon background. Space-time, this S5 times the S5 is read full with expectation values of the Ramon-Ramon fields. So that's why, actually, nobody has been able to analyze string theory directly in the type 2 string. Because these Ramon-Ramon fields make it so complicated. People have struggled. My friend Nathan Berkowitz in Brazil has produced the best sort of actions for Ramon-Ramon fields. And it's an open problem. If anybody finds a good ways to quantize the string on Ramon-Ramon backgrounds, it's a great advance. It's really holding up the field. The fact that people can't quite compute string theory with Ramon-Ramon fields. It's a great problem. Anyway, now, basically, if you want a superstring, you have to truncate. So we have to choose truncations here. And now it becomes a little bit of an interesting game. What truncations can you do? Oh, we're already in the bottom. So I'm going to truncate the following way. I'm going to say that we're going to take on the left ns plus and r minus. And on the right, I'm going to take ns plus and r plus. Now, I never take ns minus because I want to get something with supersymmetry and no tachyons. But people have tried to understand what you get with ns minus, and you get some string theories. But they're not very popular because they have tachyons and nobody understands them very well. Anyway. But there are tachyons in superstrings, and those come from there sometimes. So we do this. So we're going to have ns plus, because we do this with this, then this with that, this with this, and this with this. Those are the 4 sectors. ns plus, r minus, ns plus, and r minus, r plus. So let me write the massless states. So ns plus, what do we have there? Okay, you can have ns plus, the lowest state of ns plus is this b. So it's b minus 1/2 bar I on ns left. Now I have to distinguish. There's a left ns vacuum and a right ns vacuum. On the left ns vacuum adds the barred oscillator like that. And I have also a b minus 1/2 j on the right ns vacuum. How many states? And this satisfies level matching because this is a massless state. And this is a massless state as well. So the mass squared on the left and right are the same. So the numbers, the corrected numbers operators are the same. Everything is fine here. Now, how many states are there and what are they? So this is the NSNS sector. Well, at the end of the day, there's just 64 states here because you have I and j can be anything. So this is not really any different from having a alpha I minus 1, alpha bar minus 1 J that we had in the bosonic string. These states match. They must be the same thing. You have 64 states here. 8 times 8. And they must contain, just like in a bosonic string, a graviton from the symmetric traceless part, a Kalb-Ramond field from the antisymmetric, and a dilaton from the trace. They must all be there. So here we go, and we have a symmetric traceless tensor. How much is symmetric traceless? This is 8 times 9. Symmetric traceless is 8 times 9 over 2 minus 1 equals 35 for a graviton. Antisymmetric is 8 times 7 over 2, 28 for a Kalb-Ramond. And 1 for a dilaton. And this better add up to 64. Do they? Yeah, they do. So that's it. The NS-NS sector contains the same fields as the bosonic string. It's universal in string theory that gravity comes together with a B field, comes together with a dilaton. It's the beginning of what people do in generalized geometry, in which that universality is exploited to try to describe a new geometry. Okay, next step. NS plus R plus. B bar minus 1/2 NS left. And what do we put here? An R plus, so this would be a Ramond vacuum, a bar, because that's F equals plus 1 on the right side. The mass squared here is 0, the mass squared here is 0. This is a good state. These are how many? I, 8 values, B, 8 values. These are fermions, and there's 64 states of fermions. There are 64 more fermion states here, and this would be RA, because F is minus 1 on the left, times B minus 1/2 I on NS right. This is 64 more fermions. And here, Ramond. This is RA on the left times RB bar on the right. And these are 64, because it's 8 and 8. 64 bosons. So, 128 bosons, 128 fermions. We're in shape 256 states total. This is type 2A string theory. This theory we've built is called type 2A superstring. This fermion actually, I can tell you in a little more detail. There's one Neveu-Schwarz sector has some sort of one type of Ramond fermion, one chirality. This has another chirality. So at the end of the day, both chiralities are present, and it's a non-chiral theory. When you have a fermion and you have both chiralities, it's non-chiral theory. So this is a non-chiral theory. So actually, in here, there's what is called a Majorana gravitino and a Majorana dilatino. So it's a Majorana gravitino. The gravitino is a fermionic particle, this partner of the graviton. It's a field that has a space-time Lorentz index and a spinor index. A spinor, like a Di Latino, just has a spinor index. And these are Majorana fermions. Then there are the 64 bosons. Now you need to know some SO8 representation theory to figure that out. In a little more advanced course in string theory, if we had 2 more lectures, we could do that. But let me tell you what the answer is here. People say that the 8 times the 8 prime, so we call this the 8 and the 8 prime, because there are 8 states. In group theory, they write it as 8 plus 56. 8 vector plus 56. So actually, they say that actually you get a vector field. So you get a Maxwell field like an A mu, and a 56. What could be a 56? What has 56 degrees of freedom? Try the following, an antisymmetric thing with 3 indices. 3 antisymmetric. You now know Calb-Ramond, so you would guess that to count the degrees of freedom, you just count the antisymmetric Leibniz one. So it would be 8 times 7 is antisymmetric, times 6 over 1 times 2 times 3, and bingo, it's 56. So it's an A mu and an A mu nu rho. 3-index antisymmetric tensor. These are the fields, the Ramond fields. Here, what did we have? We had the metric G mu nu, the B field B mu nu, and the dilatant. And here we had the gravitino and the dilatino. And these are Ramond fields. Now, what do Ramond fields do for a living? That's the question that Joe Polchinski answered. And what does the Calb-Ramond field do for a living? Actually, it couples to the string. It gives the string charge. So these objects couple to new kinds of d-branes. Just like a particle couples to a Maxwell field, the kind of particle that couples to this Maxwell field is a D0 brane. So this couples to D0 branes and to D2 branes. You always need one more index than the spatial dimension of the brane. So this is related to D0 branes, and this is related to D2 branes, stable branes. Okay, we have to do the other superstring. So the other superstring is obtained by combining ns plus with r minus on the left. So that's the same as that, but then here ns plus with also r minus, not a different fermion, but the same one. So the ns plus sector is just the same as before. Then you have the ns plus r sector, r minus, and then the r minus ns plus. Now, I won't bother to write them. They're really very similar in that you have here R and R, but this time it will be the same R. So here you'll have like an RA, and here you'll have an RA on the left, here on the right, NS, NS here. Again, you get 64 fermions and 64 fermions. And what is the difference? The two of them have the same chirality. They're the same type of fermion. So if the two of them have the same chirality, you get a chiral theory. And therefore, this has what is called a Weyl gravitino and a vial dilatino. The Ramon things are different. RR, you would have RAL and RB, right. Again, 64, but now you're not multiplying an 8 times an 8 prime, but rather an 8 times an 8, because they are the same. Now, this 8 times an 8 gives you 1 plus 28 plus something called a 35 plus. It's a crazy field. So 1 degree of freedom, that better be a scalar. So we write it A. 28, what is 28 in this world? It's a Kalb-Ramond. So it's just like getting another Kalb-Ramond field, which is an A mu nu. So the type 2 theory has like 2 style Kalb-Ramonds, but they're very different. The Kalb-Ramond field couples to strings. This Kalb-Ramond field, not Kalb-Ramond field, this RR field of the same structure must also couple to one-dimensional objects. So it couples to D1 branes. D1 brane is a brane that looks like a string. So it couples to that thing. And then you get the 35. Now what could be, 35 plus, like it's exotic. What could be a 35 plus is the A mu nu rho sigma, 4 indices. Do we get 35? No. You get 8 times 7 times 6 times 5 over 1 times 2 times 3 times 4. This and this, 4 and 8 is 2. You get 70. But this field, this 35 plus, means there's some sort of duality condition that cuts the degrees of freedom of the 70 in half. So this is what is called a self-dual 4 form. Self-dual 4 form. It's a very strange field. It's so strange, that field, that nobody to this date has been able to write a Lagrangian for it. You would say, that's crazy, but it's really true. Nobody has been able to write a covariant Lagrangian. A Lycos Lagrangian you can write, but a covariant one can't. And people like to write covariant Lagrangians. We all like square root of GR and F squared. These are nice things. That can't be done for that field, and people have agonized over that. Again, another complication of Ramond fields. Yes?
Just I have a question. Presumably there must be some universal prescription how to decompose the states with higher masses onto similar fields.
What do you mean the states with higher masses?
So that have many
oscillators?
Yeah, many oscillators.
Right. Yeah, we could build all of them and do the group theory of all of them. It's a long story. It's fun to do, but I want to say one more thing. Just as a Maxwell field couples to a particle, a 2-index field couples to a 2-dimensional object, this thing couples to D3 branes. And these are the famous D3 branes of type 2B theory. This theory is called type 2B theory. That's the one for the ADS-CFT correspondence. And there are D3 branes. And you put a lot of D3 branes, and that creates the ADS geometry. With a lot of D3 branes, you're full of, they are sources for this field. So this field gets excited. There's a big energy on this field. So the Ramond field is the key to producing the background. And unfortunately, because we don't know how to do string theory yet well in Ramond backgrounds, We cannot compute all kinds of things we wish to compute. Daniel.
So if you want an invariant Lagrangian for that four form, how come you can't just take the norm of that squared like you do for the Maxwell field?
Because the self-duality condition, this four form satisfies a condition. There's a five form, 1, U2, U3, U4, U5, which is, well, I'll write it in differential notation. A 5 form, which is the exterior derivative of this 4 form. But this 5 form, the constraint is that it's self-dual. So the Hodge dual condition. And that condition cannot be implemented in a Lagrangian. So if you write that it's self-dual, you're imposing a condition that should come out of the Lagrangian itself. This should be part of the equation of motion, this condition. And that's what nobody knows how to do.
You can't just take F wedge F.
F wedge F will not produce this constraint.
Okay.
And if you try to produce this constraint, you put a Lagrange multiplier, and then the Lagrange multiplier starts propagating, and you have to kill it. It's a classic problem that people have worked very hard on. And that doesn't mean there's no clever solution, but presumably people will need a new idea. So those are the superstrings. I want to say a word about the heterotic string, and then conclude this course with a 15-minute discussion on D-branes. And it's really going to be just a word. The heterotic string is a superstring, but has less supersymmetry than these ones. These closed superstrings have the maximal amount of supersymmetry. This has less supersymmetry. And it is constructed in the most crazy way possible. What they discovered in string theory is that you tend to do the same thing on the left and on the right. And that's sort of necessary for the theory to be consistent. But you can push that to a limit. You can tensor something on the left with something on the right that is pretty crazy. So the idea here is to tensor on the left, tensor right, on the left to put a bosonic string that has no Ramond and Navier-Schwarz sector, and on the right to put a superstring. So the right is conventional, but in the left is a crazy bosonic string that you're going to tensor with the right. That superstring here is standard, so it has two sectors, an NS plus sector and an R minus sector, as you're familiar. But on the left, you have a strange bosonic string. It's so strange that you can only describe it with 8 normal coordinates. You see, a bosonic string has 24 transverse coordinates, xi's. And this bosonic string is so crazy that there's 2 ways to describe it, with 8 xi's and a lattice, a 16-dimensional lattice, the root lattice of the group E8 cross E8, or the root lattice of the group SO32. And lattices describing the bosonic string are very interesting, but people found that there was a tricky way to do it with fermions. And remember, the Navier-Schwarz fermions just gave you bosons, so there's a possibility that you use fermions and you just get bosons. The thing that you want to get from here is bosons. So what ends up happening is that this 16 xi's exotic, 16 xi's that live on a lattice can be replaced by 32 fermions. remember in the Ramond or Never-Short sector you had 8 fermions, but here's 32 with an index A that runs from 1 to 32 fermions. And given that you have fermions, now even though you're doing a bosonic string, you will have to write some sort of NS sector and an R sector. And you will call it NS prime sector and R prime to distinguish it from here. And then you will write all those states. And the question is, they ask you to write all the states in the NS prime sector. In order to see that you're getting the right answer, I'll tell you that for n perp equals 0, you get 1 state. For n perp equals 1, you get 504 states. And for n perp equal 2, you get 40,996 states. Anyway, you get NS prime states and R prime states. And you will end up choosing a plus projection and a plus projection. Now, it may be a little disconcerting that you will choose here the vacuum of this NS prime sector. As we'll tell you in the problem, the -1 to the f will be plus. And you say, that's bad news. You shouldn't do that because these NS prime sectors always have tachyons. And therefore, you're not going to get rid of the tachyon when you do this projection. But here's something nice. There's a tachyon here, but there's no tachyon here. So you cannot form the closed string state because you don't satisfy level matching. So it's okay to keep that, and it will be useful to keep that. So it's a little different how it works, but then you will construct all the states. Now, I'll tell you that the heterotic bosons appear from all the left sector, left, tensored with NS plus here. And the heterotic fermions appear from all the left states that you get, these ones and these ones, tensored with R minus. Now, you would say, look, there's something very wrong here. R always gives me fermions. What's wrong with this? What's wrong with this is that the fermions that you think you're getting from R are spinors of SO32. But SO32 has nothing to do with our Lorentz group. It's spinors in the hidden space, this mathematical space. Our real space are the 8 x's. So you're not getting spinors of space-time, but you're getting internal spinors. In space-time, this will have Lorentz indices as well. So everything will work out. It will be not a great challenge, but a little bit of a challenge to do this. And I think you will learn how to put everything together by doing this. Okay, so last thing, I want to tell you something about D-branes. Happily, we know enough that this is not complicated. DP brane. What is a DP brane? It's a brane that has p spatial dimensions. So if you think of all your coordinates of space-time, x0, x1, up to xp, and xp plus 1, up to xd, the D-brane fills the first p directions because it fills p spatial dimensions. Let's say they're the first ones, And it's certainly time exists for the d branes sitting there. So these are what I call dp tangential coordinates. Tangential coordinates. Coordinates tangential to the d brane. You know, if you have x, y, and z, and you have a d brane here, the d brane is along x, along y, but not along z. So x and y are tangential coordinates, z is a normal. So all these are normal coordinates. So I will change notation here when we talk about the strings. The string coordinate is the x mu of tau and sigma. We'll have therefore the x0, the x1, the x2 up to the xp, and the xp plus 1 up to the xd. And we'll call these ones xa, with a running over d minus p values. You see, there are a total of d spatial dimensions. There are p spatial dimensions taken by the brane, so there are d minus p spatial dimensions normal to the brane. And here, this we always called x plus and x minus, and these are always free boundary conditions. You see, the open string endpoints can move freely along the branes. So these are going to be free boundary conditions. And these are also free boundary conditions, and this will be called x capital I, with I runs over p minus 1 values, because it's the p dimensions minus 1 here, p minus 1 values. Now, the open strings can't move in the normal, the endpoints can't move in the normal direction. The strings can. The strings can be a little bit on the brane and outside the brane. So these coordinates xa of tau sigma star, where sigma star is 0 or pi, must be fixed at some numbers that we can call xa. There are Dirichlet boundary conditions. And here you would say at z, the coordinates z at the endpoints must be 0, because it must be fixed here. We can put some numbers xa. And so these ones are Dirichlet. And these are the free boundary conditions. The endpoint can move again the same way. So this is Neumann, or free. I just need one more blackboard to finish. So I guess I'll do it here. Maybe with a middle one. So, what happens here? We've studied the free boundary conditions when the brane filled all of the world. Every coordinate was free. So the only ones we don't know are these xa's. So if we use the boundary conditions, we find that the most general expansion is the following. xa plus square root of 2 alpha prime, sum from n equals 0, different from 0, 1 over n, alpha n a, e to the minus I n tau. And we used to have cosine of n sigma. And that was good because the derivative with respect to sigma was sine and vanished at the ends. But that was a case of free boundary conditions. So cosine is not good anymore. We need that at sigma equals 0 or pi, x becomes xa. So here you should put sine of n sigma. And then that's all. Another thing that you should note is that this makes xa of 0 or pi be xa, and we could not put a pa tau as we used to have in the free case. field on the brain. I'm going to use the 11/3, and we're going to finish. What else do you get? These ones, these are also very interesting. Alpha minus 1a on p plus. What are these? Does anybody venture to say what kind of field that is? If you know, if you've learned this before also, you can say, what kind of field is it for the brain, that person that lives on the brain? Does it have a Lorentz index? Is a Lorentz index on the brain? No, because it's not a coordinate on the brain. So for the person who lives on the brain and doesn't see anything, this is just a number, a label. So these are scalar fields, massless scalars. So you get one massless scalar for each normal direction. Now, I ask you to now switch gears. It's a very important change that is happening here. We started with open strings, and we put a boundary conditions, and we said, OK, there are things called branes. In some sense, the branes come before the strings. And I will say it this way. You should really probably think of open strings as excitations of the brain. You have a brain with no excitation, is static. You have a brain with open strings attached, the brain fluctuates. That's interpretation. If you have a tachyon, it's an instability on the brain, excitations that reduce its energy and eventually destroy it. And this, one massless scalar for each normal direction, you have the brain like that, or we had it here, and you can excite that scalar field in the normal direction, and the brain bends a little up and fluctuates. These scalar fields correspond to excitations of the brain, and they're massless. Imagine the brain sitting here, and the brain a little displaced up. It's the same energy state, because the energy doesn't change. And the displacement is uniform on the brain, so it has no momentum along the brain. So it's an excitation with zero energy and zero momentum. And an excitation with zero energy and zero momentum is a massless excitation. So these scalar fields that live on the brain, those strings, are the things that allow the brain to move. So this is the most important result of brain theory. There's one more result, that is, if you have several D branes together, you get a Maxwell field for any string that begins and ends on a D brane, but you get another Maxwell field for one that begins and ends on another D brane. And the ones that end on different D branes. So if you have an open string now, you can say, if you have n D branes, coincident, you have open strings that begin on the ith brane and end on the jth brane. So you get a Maxwell field for all of them. So you get Maxwell fields that have two more indices. And these indices are nothing else than the Yang-Mills indices. People who have discovered Yang-Mills theory and branes. This actually, with n D branes, there are n squared fields. They can start in one, end in one. Start in one, end in two. So you get n squared gauge fields. And it's a UN theory. So non-abelian gauge theory, you got the Maxwell field, you put several D branes together, out come non-abelian gauge fields. And it's a very intuitive picture of non-abelian fields. The indices of a UN field are now thought as branes, and it gives you a picture. So we've come to an end. I hope you enjoyed. I did enjoy a lot. It was nice to get to know you. I'm going to leave in about 15 minutes. I'm sorry about that. I wish you the best of luck in your continuing studies and to see you sometime again here or anywhere else. Bye.